All right, hey everybody. I'm recording double time on this because this is going to be kind of a long lesson, and I've been having a weird issue where things get deleted and stuff. So I'll either post it like normal and everything will be happy, or if it doesn't work, I'll post the video in another way that I know how. But that's besides the point. The reason I am being so careful this time is because this is probably going to be one of the longest lessons. It's the last major thing. Yes, after this, we have 2 more lessons that deal with this type of thing, but this is the one that is going to take some time to get used to. But once you get it, it looks the same every time. So this is the least creative type of problem you'll see on the AP test. But it's the one that takes a while to kind of wrap your mind around. So it's called volume by rotation. So here's the idea. We've been finding the area under curves to do real world accumulation type stuff. And then we've also, in the last lesson, just found the area between 2 curves as like area. So you can find the area of a triangle like we did, in problem 4 of the homework, using calculus and integrals. Well, turns out there's something even more weird and interesting you can do. I go a little more into how this works in Calc BC, just because it's one of those things where if you really want to know, I'd love to tell you, but I'm kind of going to skip some of the theory behind it and just show you what you're doing and how to do it and show you how the calculation works. It's not hard to talk about, but this video is going to be long enough anyway. And we're kind of wrapping up, getting close to the AP test, so I want to get you into these types of problems as quickly as possible. Okay, so here's the idea. You ready? It's called volume by rotation. I give you a function. So in this one, I have given you y equals x. So you'll see something like given y equals x, in this case, that's your function, from x equals 0 to x equals 3. That's the setup. Find the volume of the solid generated when the function is, ready for this one, rotated about the x-axis. So what? So we're taking this shape. There it is. So here's the function from 0 to 3. See how I have it stopping at 3? And here's what's going to happen. I'm going to rotate it around the x-axis. So this solid, imagine it rotating and coming out at you. Why am I using this window? Because I'm actually going to be able to simulate it pretty nicely with this. So don't miss it. Ready? We have it. All right. So here we go. Revolve. Check it out. See how it's rotating it? And look at the shape you get. It is a cone. So we obtained a solid object. I know on this one it kind of looks like it's not solid, it's hollow, but this is a solid object. It's a cone in this case. And using calculus, we can find the volume of this solid object. We can find the volume. So we're taking areas and we are rotating them around a horizontal line. Let's see if we can reset it. Reset view. Oh, no, there it goes. So there it is rotated. So I took this solid object right here, solid area, and I rotated it to get a cone of solid volume. And the goal today is to be able to find the volume, which means like cubic units of this shape. So here's how it works. There are lots of more specific strategies for this, and we'll get into those. But essentially, here's how we're going to do it. First thing, and I'm going to give you a very, 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 very specific structure for how to do this, okay? So on a simple problem like this, we're just going to kind of build it. And then as we do the harder problems, I will walk you through everything. But there is a very, very, very specific formula for doing this. So here's where the formula kind of comes from. Okay, so here was my graph. 1, 2, 3. Here's the shaded region. I rotated this around the x-axis. So think about taking just one little sliver of this and what it would look like if you rotated it around the x-axis. You would get a bunch of discs kind of stacked on top of each other, a bunch of CDs of different sizes stacked on top of each other. That's what this really is. So really what we're going to do is we are going to add up a bunch of super skinny discs. That's the plan. Add up a bunch of super skinny discs. So let's talk about one of these discs. The area of a disc is equal to, what's the area of a circle? Pi r squared. The area of one of these circles, area, because think of it, it's infinitely skinny. So don't think of it as it has a height. Think of it as it's a flat circle, and we're finding the area of it. So the area of the disc is pi r squared. So now the big question is, what is r in this? This value right here, r, is equal to the function. Most times it's going to be equal to the function. And the function in this problem was y equals x. So here's what happens. We're adding up a bunch of these. Well, the way to add up across an infinite space is the integral, and that will give us the volume. So we go the integral from where we're starting, just like we did area, to where we're stopping of one of these discs, except the radius is always changing. So instead of putting r, we put the function squared dx, because we are dealing with the function in terms of x, because it's kind of like the top minus bottom situation. We'll get more into that. So in this case, the calculation would have been 0 to 3. Pi is a coefficient, so we can put it out front. And it is the function squared. And the function was x squared dx. And that is how you would calculate the volume of this specific shape cone that we just showed you in the simulation. So let's check it real fast. So you have pi int 0 to 3 x squared x, 28.27. Now, in case you didn't know this, the volume of a cone has a formula. It's 1/3 pi r squared, and the r is the top, the biggest of the cone, the biggest piece, so that's 3. So 3 squared, which is 9, times h, and h is the height. So the height is this one, so times 3. Same answer. So I always like this. I made you do this on the discussion. You can check that, yeah, this calculation that we used, that we got doing calculus is the same as what it actually is when you find the volume using geometry. So geometry, volume of a cone is 1/3 pi r squared h. Calculus, volume of a cone we got by rotating a linear function around the x-axis and finding the volume. All right, that's the idea. We are going to practice this a bunch. So also keep in mind, this is the last major thing we're doing. We will practice this for the next month. So it's just like anything in this class. We just have to keep doing it. It's really hard at first, especially with all the different variants you can see. It's going to take some time. Okay, but remember this formula where it's kind of like pi times the function squared with your bounds, and it'll make these problems easier. So let's do another one and see how the formula can help us. So example, whoa, hello, let's erase that. I wonder if it's moving so slow. All right, so example, nope. Example, find, well, that's a V. Zoom in. Find the volume of the object obtained from rotating y equals x squared from 0 to 4 about the x-axis. Okay, so we're going to take x squared and we're going to rotate it. So if we go back to this simulation and I reset it all, what kind of weird shape are we going to get with x squared? So x squared, this time I changed it from 0 to 4, 0, set functions. It's the parabola. This one's kind of cool. So from 0 to 4, I'd have to change the window. Let's reset the window a little bit. So x max, let's go to 10. No, I lied. That one's fine at 6. I meant to change the y. Negative 10, 10. Right, because it's at 16. Whatever, doesn't matter. Okay, so watch what I get when I rotate this thing. Ready? Whoa. It's kind of like a satellite dish. So I'm going to find the volume of this volcano almost, this satellite volcano. And again, I know it looks hollow on here, but it's not actually hollow. It's a volume or like a top or a tornado or something. So you can get some really interesting shapes and you can find the volume of it. So for manufacturers that need to produce or like buy material to make objects, you can find the exact volume. Another way to do this is by displacement, like buoyancy, or what is that called? Water dispersion, where you put something in water and figure out how much the water tank rises. That's one way to find volume. This is cleaner. If I can graph something and then rotate it, I can find the shape and then I can find the volume of that using calculus. That's the idea. All right, so I'm actually going to give you the steps that you should start to use. So this is going to be the major approach. So this is the one to pay attention to, and the next one, because these two are going to build the two types of problems you can expect to see. I'm going to give you my steps for doing this. So here we go. Step 1, graph, shade, find bounds. I would always start there, just like you're doing an area problem. Graph it, shade it, and find the bounds. So the graph looks something like this. Doesn't have to be perfect. And it goes from 0 to 4. Oops, let's do it this way. And then shade the correct way. So we're rotating, which I'll talk about that in the next step, top to bottom, because we're rotating like this, just like we did on the last one. So we're rotating this whole region. So yeah, you can kind of shade this one, just to know that that's the region we are rotating. What do I mean by find the bounds? I mean from where you are starting to where you are stopping. Okay, the second step, and this isn't going to make sense until the next lesson. This lesson is all about a horizontal axis of rotation. So that's the question you ask yourself. Horizontal or vertical? Because guess what? Next class, we're going to rotate this direction. Vertical axis of rotation. But this is horizontal. Anytime you see x-axis or y equals something, that's a horizontal axis of rotation. If you see y-axis, or if you see x equals something, that's a vertical axis of rotation. So what are we doing in this problem? Well, I've told you today everything is horizontal. And yeah, it says, look, about the x-axis. So that means horizontal axis of rotation. So we are doing a horizontal axis of rotation today. Why, or in this problem and for the rest of the day. Why is that so important? That tells you what variable to use in the problem. So just like when we did top minus bottom is always x and right minus left is always y, horizontal, you're going to use x as your variable. So we now know what variable we are using in the problem. So then I say step 3 is this very important question. Step 3 is going to be how many, can you see that? Let's come back here. How many radii? And the question to really ask yourself is, do you see blank space? Now, let me explain to you what that means. We're rotating across the x-axis. So I'm going to go back and put the line right here. the entire shaded region, this blue shaded area, is sitting right on top of the x-axis. There's no space between the two. So the shaded area right here and the line I just drew, the dotted line, there's no space between them. They are touching the entire time. So the shaded area and the dotted line, there's no space between them. So if there's no space, there is one radius. If there is space, which will be on the next problem, we're going to have two radii, and we'll see how that works in a minute. So in this problem, there is no space. So if there's no space, we only have to worry about one radius. So then step 4, find the radius or radii. Using this idea. Here's how you find the radius, and I'll do it with one radius in this example, and I'll do it with two radii in the next example. And the next example, we're going to do a bunch of different ways. So one radius, start at axis of rotation, go through shaded area, stop at outer edge. Okay, so I'm going to draw what I just said. Start at the axis of rotation, right here. Through the shaded area, stop at the outer edge. That distance right there is the radius. I'll do it again, and I'll draw it in a slightly different spot. This distance, there it is, the radius. Starting at the axis of rotation, through the blank space, or sorry, through the shaded region, stop at the edge. One more time. Axis of rotation, through the shaded region, stop. Now look, the radius is always changing. So each one of these looks a little different. But again, that's fine. In calculus, we deal with change all the time. Just because the radius is changing, that just means we have to talk about it in terms of the function, not in terms of a numerical value. So in this case, the radius is just the function. It's f of x, which was x squared, just like the last problem. So I have found my radius. My radius is equal to x squared. So finally, I can do my setup, the payoff moment. So step 5, do your setup. Here's what the setup looks like. The volume equals, start with a pi in front, because it's part of your formula. From your start x to your end x of your radius squared, dx. And plug everything in, and you have your setup. So in this case, it is pi 0 to 4 x squared dx. And that is the volume that we plug into Desmos. So you pull up your Desmos, or you pull up your calculator, and in this case, it's 4x to the 4th. 643.398. 643.398. That's the volume of that crazy satellite dish thing. I wonder if the other website actually got that answer. Oh yeah. So this thing's pretty cool. 643.398. All right. It also found the surface area. We're not doing that. So that's the idea, okay? We will do lots of examples, but this is the process you're going to follow. So we're going to now try it with two radii, okay? So let's try this again, but a slightly different problem. Check this one out. Find the volume obtained by rotating the area enclosed by y equals x squared and y equals root x about the x-axis. All right, so we have our setup volume obtained, we're rotating this area. I didn't give you a start and a stop, which means you're going to have to find it yourself by finding the intersection points. So step one, let's graph it, and let's find the intersection points, or the bounds. So here's one, here's one. Remember, these ones do this. We saw these last video, something like this. So here's y equals x squared. Here's y equals root x. Okay, where do they intersect? At 1, 1. So the bounds are from 0 to 1. So I like to do this sometimes. The x bounds are from 0 to 1. All right, we have our bounds. We have our graph. Let's get a little shaded area going. Cool. So next lesson, we're going to rotate vertically this direction. This one we're rotating. I mean, you could probably guess you're going to get the same answer both ways because it's symmetrical. But that's fine. That'll be something we do next time. All right, so that's step one. Step two was that important question. We'll come back over here. Horizontal or vertical? Well, I told you today it's all horizontal, but you really need to start locking this in now. It's not a hard thing to know. You just got to pay attention. It's horizontal because it's the x-axis, which tells me to use x. Cool, so I know I'm using x's. I'm using these x bounds in this problem. All right, step three. How many radii? Here's the new part. So again, you see what we're rotating about the x-axis? Boom, 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 boom. Is the entire shaded area, if I go from the shaded area down to the dotted line, do you see any blank space? Yes. Here it is. Here's what I mean by blank space. This is always hard to classify for students. It's this. If I drew a straight line from here to here, you see all this? That's what I mean by blank space. One more time. You see all this? That's what I mean by blank space. So there is blank space in this problem. So yes, blank space, which means we're going to use 2 radii. Radii is just the plural of radius. All right, so now the hardest part, part 4. We need to find both. So now we have 2 radii, and we're going to talk about it a little bit differently. We're going to talk about big R as radius 1 and little r as radius 2. Okay, so big R. Here's how you find big R. Start at axis of rotation through blank space, hit inner edge, through area, stop at outer edge. Okay, it's a lot, but I'm trying to be very specific because these can get a little weird. So here we go. Start axis of rotation. Through blank space, hit inner edge. Through shaded area, hit outer edge and stop. I'm going to draw it one more time. Start at axis of rotation. Through blank space, inner edge, shaded area, outer edge, stop. Those are your big R. And what is that? That is the outside function or the top function. Most of the time it's the top function. So the top function in this case is radical x. So in this problem, big R is the function again. How about little r? How do I find little r? Start at axis of rotation through blank space. Hit, I guess I should say stop. stop at inner edge. So what's happening here? We are ready. Let's do it. All right. So in this case, start here, through blank space, stop at inner edge. Bam. So little r is this little distance, and that is equal to the other function, x squared. So in this case, when we're rotating around the x-axis and we have two functions, you're basically going to have one of them as your big R and one as your little r. So finally, step 5, we can do my setup. The volume is pi integral 0 to 1, your bounds. Now, the formula looks this way. You do it like we did last one. It is the radius squared. But think about it this way. We're cutting out. We want to exclude that inner part. So we want to do big R squared minus separately little r squared dx. So it would be pi 0 to 1, the big R, which is root x squared, minus the little r, x squared dx. That's it. Come to Desmos. That's the hardest part. Oftentimes the FRQs will literally just have you setting it up. They won't even ask you to evaluate it because the setup is the tricky part. At this point, you could just plug into you could just plug into Desmos. Let's just do it this way. X root squared is just wow. Come on. Square root of x squared is just x minus x to the 4th dx. Tiny little thing. When we're rotating it, we get a weird kind of, I don't know what that even would look like. It's a weird kind of bowl with like a groove cut out of it this way. Pretty sweet. We could go to the rotator thing and play around, but we're not going to. Okay, so that's what we are doing for the most part. So let's do some other really difficult problems. So we're 27 minutes in, I get it. I would do your homework while you watch me do another one because these are difficult and they take time. And there's so many different ones, but let's see if we can follow my same logic. I'm gonna do 2 more. So I'm just gonna say volume, find volume, obtained by rotating region enclosed by y equals 4, y equals x squared, and y axis about, and we're actually going to do 2 different problems, and that's what I mean. We'll do both of these and then that's it. First one, about the line y equals -1. Okay, so there's a lot going on here. Let's go through this very carefully. So first thing, I'm going to kind of combine some steps together. I think you should definitely take this step by step. Otherwise, this just feels overwhelming. So I am rotating y equals x squared. So it looks like this. Y equals 4 and the y-axis. So here is my shaded area. What are the bounds on that? It starts here at 0. It stops here at 2. So from 0 to 2. That's my x bounds. We don't need to worry about the y bounds today because we're not doing any vertical rotations yet. Okay, so that's my prep. I have found my area. I have found the bounds. I'm ready to move on. Step 2, I'm going to kind of combine step 2 and 3 at the same time here. So first thing, horizontal or vertical? Well, we're rotating around y equals -1, which is down here. And that is a horizontal axis of rotation. So horizontal, which means I'm using x. So sometimes I'll do this. Pi, 0 to 2, x bounds, and then dx. I like to build the answer as I go. Next question, do you see blank space or not? Definitely. So look, from 0 to 2, that graph is not even touching at all. Not even touching at all the axis of rotation. So I'm going to have 2 radii, something squared minus something squared. This one is going to be your big R. This one is your little r. Okay, so that's my setup. Let's do this. Let's move this over so I have plenty of room to work. Okay. I like this approach where you build the answer, get it all set up and ready to go. And now the hardest part is just finding the radii. So I won't write that down again. We wrote it down earlier, but you can reference it. To find big R, start at axis of rotation through blank space, hit inner edge, continue through shaded area, stop at outer edge. I'm going to draw it one more time. Through blank space, hit inner edge, through shaded area, stop. In this case, big R is the same no matter where I draw it. Big R is not changing, and that's because the top function is constant. So when the top function, which in this case was y equals 4, is not changing, it's a little bit easier to think about. Just look at that distance. How big is this distance? It's 1, 2, 3, 4, 5. Now look, it's not 4. It's 5, and then it grew by 1 because we are rotating it down a little bit. We have put kind of a hole in it. So big R in this problem is 5. You need to understand that topic right there. Big R is 5. That's why I'm a really big fan of you drawing it and drawing your radii. Big R is 5 in this problem. What about little r? Here we go. Through blank space, stop at inner edge. Let's draw it one more time. Through blank space, stop at inner edge. Well, here's the hardest part that students always mess up. This whole distance right here is little r. Well, what on earth is that? This distance from the curve to the x-axis, so this distance right here, that distance is your function. So that is x squared. But what have we done? We have added 1 unit to it to make it 1 unit longer. So it is x squared plus 1. X squared plus 1. We've made it 1 unit bigger. So anytime you rotate around something different than the x-axis, your r is going to get either bigger or sometimes smaller. Got to really pay attention to how r is changing, how that distance is changing based on where we rotate it. Another way to think about this is if the top curve was 4, and then it's top, you can kind of almost think about it as top minus the axis of rotation. So 4 minus -1. So same thing here, x squared minus the axis of rotation. It's another way to think about it. But I like thinking about it in terms of distances, especially because of what's happening next. And then once we've done that, that's the setup. That's it. So in your Desmos, which we're not going to do for the sake of time, because like I said, the hardest part of this whole thing is just getting the setup. That would be the thing we plug into Desmos. All right, let's do one last one because we're at 33 minutes. Like I said, this is a long video. We're going to do the same exact setup, but let's try one last one. Let's rotate around y equals 6. Okay, so same setup. Rotating around y equals 6. So here was the graph again, didn't change. Everything about this is still the same. Typically the FRQs will do this too. They'll keep it the same and then they'll just change rotation type stuff. Here's what the problem looks like. So again, the x bounds aren't changing, still 0 to 2 from where we're starting to where we're stopping. But this time it's going to get a little weird. So same thing, we can set it all up. We know it's 0 to 2. I see tons of blank space. So I know I'm going to have a big R squared minus a little r squared, and I know it's dx, and don't forget the pi. All right, let's build that answer. We've started, and now let's find these radii. Follow my process. I've really emphasized this over the last few years because students used to be like, I'm lost, I don't know where to start. Here's where you start. Take your pen and put it on the axis of rotation. Through blank space, hit inner edge, continue going to outer edge, and stop. Let's draw it one more time and see if it changed at all. Start at axis of rotation, through blank space, through shaded area, stop at outer edge. It changed. So this is one of the trickiest types. What on earth is this distance? Well, this distance in orange, that is always the function value. So that is your f of x, which is x squared. So what is this thing in red that I drew then? What is this? Well, think of it as the whole distance, which is 6, so the whole thing, minus x squared. It is 6 minus x squared. It is the whole distance, 6, and you're subtracting out the function. That happens when the axis of rotation is above our shaded region. So big R, 6 minus x squared. The whole thing, take away the piece. All right, and now it's time for little r. Here's how you can think about it. Start at the axis of rotation, through blank space, stop at inner edge. Let's redraw it. Through blank space. It didn't change. And this one, it's pretty easy to see, but in terms of thinking about it as functions, you could think about it as the whole thing, 6 minus this constant function here, which is 4, or it's just 2. So in this case, little r is 2. And the shape that you would get if you rotated this thing, you'd get like a molehill. You basically would get like a gopher mound with a hole right in the center, or like a hill with a hole. It's pretty cool if you think about what that actually looks like. And that's it. That is the setup. Yeah. That covers, and then that's fine. We don't need to go to Desmos. That covers the major types you'll see. If you are good, that's it. If you want to see one more, may as well. We're hitting at 40, but that's fine. This is an intense lesson. Spend some time here. Okay, so part C says, let's rotate around the line y equals 4. So one last one. Let's see if you can think your way through this one. Same setup. Nothing much changes. Here is your shaded area again. And this time, check it out. We're rotating right here. So again, we know it's a horizontal axis of rotation. So all today is horizontal. We're not doing vertical yet. So the volume is going to be pi 0 to 2 again. We're not changing the bounds. And we are doing big R squared minus, well, that's the question. Do you see blank space? No. I mean, I kind of drew it, but no, it's sitting right on top. This shaded region is sitting right on top of the, or underneath. It's completely touching the axis of rotation. And so this is only one radius. So sometimes you'll have one radius even if you're rotating somewhere else. That's why it really helps to graph it and follow these steps. So if it's one radius, we go back to those rules. Start at axis of rotation. Through blank space, oh no, I lied. Axis of rotation through shaded area, stop at outer edge. Draw it one more time to see if it changed. It changed. What is this distance? Well, let's do it one more time what we just did in the last one. This distance in green is the function. So the distance we're looking for is the whole distance, 4 minus the function, or 4 minus x squared. Done. All right, so that is the longest lesson for a reason. It's the hardest, most technical part. But once you have the idea of these crucial steps, it becomes a lot easier. So I think the discussion, I'm actually going to change it. I think for the discussion, I'm going to have you guys show me your step. I really want to see this. I want to see these steps drawn out, these ones. Okay, so this is what I need, because as we start to do these and start to do these FRQs, if you have these steps, they start to become automatic. But these can get really easy to be lost in if you don't have these steps. All right, that is it. Try the homework. Good luck.